manipulator itself is an example of a problem that we had to work out over a long period of time. Our design and actual construction was fully custom by us initially, and it just didn't perform again to the extent that we wanted it to. Over a long period of time in our manufacturing process, we were slowly able to fix the small problems here and there, eventually bringing it into a state of operation that was satisfactory for us. It involved integrating some components from a previous year's design, but we were eventually able to get it to work. One of the most interesting problems we had was very late in our actual build process, and it actually occurred during our testing. One of our Cbotics motors actually failed completely, and one of the reasons possibly being because these motors we had also utilized last year. Them being brushed DC motors, they actually have a lifespan in some of the parts on the inside. I actually had to go about fixing this problem myself, so I can tell you about it personally. I came in to Dr. Rand's house, where was the pool that we're practicing that day, thinking, you know, it'd be a smooth day of practice, we'd get some things done, we'd feel more confident by ourselves at the end. And I walk into the garage and see Cyrus, our team lead, sitting in the corner on the verge of crying. And,
it's just that, man.
And Dr. Rand, our mentor and advisor, standing in front of his workbench with a pile of parts sitting on the bench that I learned was one of our BTD 150 motors that had completely failed. And you know, we really didn't know what to do, but I volunteered to take a look at it, degrease some of the parts, and just so happened to recognize a few of the pieces inside from the physics class that I'd taken the previous semester. Realized that one of the graphite brushes for the brush DC motor had actually worn itself to its lifespan, and so I went about custom fabricating a new one from a thick copper piece and soldering it into place inside the motor, greasing it, reassembling it, and testing it to find that it was working and functioning the way we wanted to again. So, needless to say, some things were slowly worked on over the course of the project, some things were totally unexpected, but we were able to work it all out. Along with the components that I mentioned, a lot of things have to be modified. She'll uncover some of the modifications we made.
So this year's increased functionality include our manipulator, our extractor, cross-section collector, and magnets and probes. The arm is one of the most important components in the ROV. Initially, we first designed an arm which didn't work too good. So what we did, we took out the arm from last year's claw and put in this ROV. And in that way, it's really effective and reliable too, and doing all the tasks in this build. Next, auger mechanism. As Dave mentioned before, we designed a protocol that didn't work before, and we ended up getting a vegetable steamer actually, and it upside down in the back of the ROV is mounted. And we tried like 5 or 6 times, and it constantly grabbed the auger we need to grab. And it doesn't fail, it locked up by itself, it's reliable too. And one of the components is cross-section collector. First of all, we designed a vacuum at the bilge pump with a vacuum hose in it connected. And the suction wasn't strong enough to get all the lures off the wall. So what we did, we designed a fishing net, and it's going to be around it by the claw. And right underneath the net is a hose up there. The fishing nets give us a chance to get scooping effect. So the wall, when you scoop the fishing net of the wall, and the hose is right underneath the net. In that way, the lure will stay in the net, not going to fall off. And the next thing I would like to talk about is the magnets and probes. It's a modification to get the pins of the elevator. We found out that with the claw we have right now was getting too much time to get the pins out of the elevator. So through reading instructions and everything, we found out the J bolt is stainless steel. So we put a magnet right around the claw. In that way, we can save time and get the pin out of the elevator. Just in case if the magnet wasn't strong enough, we put a probe right underneath the magnet, which is basically a coat hanger that's up there. So if the magnet fails, we can still use the probe to get it out of the elevator. And it's really time consuming. I mean, you can save our time in that way too. Also, last tether protocol. Tether is one of the most important parts in the ROV. Without it, all the communication will fail. As a tether handling, I always make sure the tether is always coiled up and everything nice. Also, while the ROV is in the water, make sure not to give too much slack, otherwise it might get tangled. envelope in the water, take it out of the water, and also let the pilot know how much tether I have left to give the correct degree. And also while you practice in the water, in the pool, always make sure like tether is really nice and clean.
So ROV is a digital system, not analog. So what we have to design and implement is a control system. And when we start designing this control system, we want to make sure that we made it flexible and easy to adapt. Because they can see projects like these have problems and you need to either make changes to your components or add new ones. First thing with our control system is our pilot console. And as we said earlier, our pilot console is an Xbox 360 controller. It was chosen because it's familiar to a lot of people. It's designed for its ergonomics, and it's a USB interface, which means it can plug into our laptop for our software. And that also means that any USB device can be switched out, so it's easy to modify. From our GUI, our software, that software does all the calculations for all the thruster controls and all the controls from our pilot. And then going down to ROV, so all the things get set down to control the manipulator, the crustacean collector, the LED lights, and as well as the thrusters. We mentioned before that the thrusters are located, the four that you see on a horizontal plane are located at 45-degree angles. And the reason we position them this way is that on the horizontal plane, they have all translational and rotational capabilities. So for example, if we're doing the spire task, we can have our ROV viewing the spire and actually have it rotate around 360 degrees while maintaining view of it. And that way we can determine the best place to take temperature readings.
So as you can see, I mean, with a lot of modifications and things, we've actually reduced our costs significantly. There's three things that we felt reduced our costs greatly, and they are our H-bridges, our airtight housing, and also our manipulator. I'll start with the manipulator. Initially, we had designed a manipulator that would have cost in the upwards of $3,000, and we feel that it just went right outside of our budget a little too much. We had then decided to fabricate our own manipulator in-house, in which that wasn't working as effective as we had wished. At that point, it was getting pretty late, and we realized, last year's manipulator was working very well, so we would retrofit it onto the existing forum that we had designed earlier in the semester, and it works great now, which now costs around $60 for just the aluminum parts that are holding it together. The airtight housing was another thing that we wanted. Initially, we wanted a cylindrical acrylic tube milled out and machined by another company with our design from SolidWorks, but we had realized that that would cost it upward around the numbers of $800 to $1,000. Again, something that was outside of our budget. In which case, we then had bought a simple Pelican box that I'll show you here, where it houses just our microcontroller, and it snaps open pretty easily. Well, when the PIC needs to be reprogrammed or whatnot, it's easy to get inside and reprogram it. And since the seal is done by Pelican case, this actually is airtight to up to 100 feet, which is perfect since we only operate at 6. In which case, then we also retrofitted our own waterproof connectors from SureSeal connections. So that whole assembly only costed us around $45 to $50. The last modification that initially significantly reduced our costs, was our H-bridges. Again, in the beginning, we wanted C-Dotix thrusters with their own internal H-bridges. They're controlled by I2C and can directly interface with the microcontroller. However, those cost each around $2,000, whereas we had 5 thrusters from last year, and we only had to purchase one more. So we recycled parts and only ended up paying $400 for one thruster. And since we were sponsored by robotpower.com, we received 3 motor drivers to just epoxy ourselves. To conclude, I wanted to say that we have developed a fully functional and multifunctional, environmentally safe and stable vessel. It's safe because, again, we do not use hydraulics or any fluids, any toxic substances that could potentially harm the environment. It's all electronic, everything from the motors to everything. And it's also a multifunctional vessel. If you notice that the way David designed it, the thruster mounts are actually adjustable up and down. So we figured, since we put so much hard work into a frame, why not have it being reused for several missions? It can significantly reduce costs from having to fabricate a new one. If the payload changes, we simply adjust our thrust line for that change. Also, it's stable. Again, all the electronics are completely isolated. Microcontroller is in its own housing. The motor drivers are all encapsulated in their own design and their own housing epoxy. In addition to that, for stability, our buoyancy package, again, provides a slight positive buoyancy for, in the event, again, as I said, if data communication is lost, then the ROV will slowly float to the surface. Also for a driver's preference too. And the nature of the vehicle is bottom heavy, so in the event of capsizing, it will always right itself. I'd like to go ahead and thank our sponsors now. Kapi'olani Community College STEM Center, our advisor, Dr. John Rand, for providing his house for days on end.
I'm sorry, I'm late.
In Synergy Engineering, robotpower.com, the NASA Space Grant, Seabotics Thrusters, of course the University of Hawaii Kilo for this beautiful venue, and can't thank MAPE enough for allowing us the opportunity to be here and to compete for Aloha Sima. Thank you.
Thank you. Good job, guys. Good job. I didn't hear where the temperature reading happens.
Oh, sorry. That happens right over here, actually. We modified it to, we put a funnel in the end to capture the water, rather than sticking a probe into something potentially damaging a spire or a hydrothermal vent. We have the probe actually slide in here. It's nested inside, so we simply go over the cup, and it'll actually collect the cold or hot water in that area and give us a nice close approximation on the actually the hundreds, right?
Yeah,
Hundreds.
And using the funnel makes the task go so much quicker too. We were spending a lot of time trying to get the temperature probe inside the spire itself. Here we can just kind of go over it, and because of the funnel, we can just slide down and get very accurate readings pretty quickly. Let me show you the graph.
Sure.
Let me show you actually how we're going to graph. It's done on the GUI itself instantaneously.
Ready to serve, my lord.
So you can see again, we have a completely custom GUI. We added sounds for driver feedback. We don't have our communications enabled right now, so I can't actually show the live graph, but that happens on this section of the screen. You hotkey,
Work complete.
and you'll get a bar graph that comes up depending on the temperature, and each individual graph represents a specific depth.
Have you calibrated your temperature?
Yes.
Okay.
We just did.
Okay, multi-point, 2-point straight line.
We did.
It has a function that uses natural logs and as well as power, so it's not a linear function. But our data sheet for the temperature, the thermistor, it did come with a formula to convert the resistance into a temperature reading.
And you calibrated that yourself?
Yes.
Yeah, we did both freezing water with ISO right at 0, also boiling water, and we took a thermometer as well as our probe inside the same vat of water and heated it from 0 to about 50 degrees and made sure that both graphs or both temperature readings were accurate, and we're within 1 degree.
I'm not clear on how you get your crustaceans. That's a suction. How do you explain it?
So this is our page from right over here,
Okay.
and the dashboard.
So you have to return it.
Yeah, well, the pilot is coming up the crustacean and also the auger. In that time, we're gonna change it. Put the name here and then go down. Because he's doing the Size is doing the K business last test. So we don't need the call after that.
And it's also for strategic purposes. I mean, we're going to have to resurface to return the spire and the auger collection sample. So we felt that instead of making more additions to the frame, if we're going to return it anyway, I might as well make a minor adjustment and make it just as effective.
I didn't hear about the acoustic sensor.
Yeah, that is right here on the front. We have a hydrophone, and we're going to use third-party software to display a spectrum of the entire audio range, and it includes peak analysis and a frequency counter. So when we go in front of each spire, we're actually going to see where the frequency is and be able to measure the amplitude, and the highest amplitude wins, and that's probably will determine which spire is actually rumbling.
And how does that frequency
Is it an energy spectrum or what is it?
No, it's an actual frequency versus amplitude spectrum, so it's a real spectrograph.
Now, the power for these two systems, how is that done?
Oh, yeah. For the hydrophone, actually, it's sent up through two auxiliary lines up our tether. It does not communicate at all with our microcontroller. So it's sent up analog, in which it's digitally processed through the microphone jack on the computer itself. The temperature probe is done through the PIC and sent up data packets to the outside computer.
Okay, but is that power isolated in any way?
No, it's just signal lines for the hydrophone itself. So as its acoustic pressure is being created, it'll send up its own signals, and where the gain of it will be amplified in here.
But the thermal probe is actually tied to the same power line as your motors.
Oh, I'm sorry. Yes. It is through a 3.3 volt regulator inside here, where we've done actually an attenuator circuit to get the voltage.
Okay, so you don't get voltage sag on them.
No.
I must have been sleeping through your discussion of cameras. How many did you have on? Four.
We have a forward view, a top view for depth perception, as well as a side view for entering the cave, and also an auger view for extracting the auger.
Can I color it black and white?
Color cameras.
All color.
Yeah, I didn't say
Was
there's
it
so
very
many
good?
different elements to talk about on the ROV. We had to really kind of cherry pick the key features that we wanted to emphasize.
And how do you display those images? Is it on the same GUI that you're using here, or
No, actually,
do you use separate monitors?
the part we wanted was, of course, a component to USB, in which case we'd have one more monitor, like a surveillance cam type deal. But part came in a little late, and so we ended up just using our own monitors from last year with an analog video switcher.
So your frame has these extra spires above sort of the top rack. When your phone pack is in there, they're even kind of a little taller than the phone pack. What's the purpose of those?
We had actually had a larger design than this. Our initial frame was taller than this. After taking a look at the dimensions of our cave, we decided, as well as taking a look at the components that we were going to have inside of our frame, moving the thrusters in and seeing how the space would work out, we decided to reduce the size. So this is the point actually at which we had cut down the frame and when we were initially testing, our styrofoam package was actually the entire area of our vehicle, and these spires are left to help protect it because it's a fiberglass encased styrofoam, and so some hard impacts are still capable of compromising it. So we wanted to have a little bit of protection, at least in the corners, and we left that there even though we had ended up modifying our buoyancy in order to reach our essentially neutral or slightly positive level.
What is the C right here?
The probe.
Yeah.
Oh, the probe.
It looks like smoke.
I was taking a break. So this is the magnet attached to claw to get because this is stainless steel,
Okay.
and if it's not strong enough, we use the probe to get it out. It's a jailbolt.
Yes. I'll actually approach from the side.
Yeah,
see.
the driver from the
Okay.
side, I'll
Okay.
take it out.
Okay, gotcha.
Yeah.
And what is this silver thing I can see on the side?
This
Yeah.
is actually a mirror, so we can use our side view mirror to look backwards as well.
For the most part, everything that looks really nice was engineered into the project. Everything looks like it was jury-rigged. Actually, we're doing all the practicing, figuring out what can we do to give us the best time possible.
Just so happens all of our jury things work very well.
So your tether, how many conductors is supporting your tether? You mentioned it.
Yeah, 15. So we have actually 9 signal lines, 2 power and ground, and let's see, maybe 15. Let me count that again. 9 signal lines, 4 coaxial cables, and actually power and ground. So 16. I'm sorry.
What are the 9 signal lines?
Well, there is 5 auxiliary. Sorry, actually, no, there's, because of the audio, let's see, there's 4 for the UART connection, 2 for the audio, and then 3 auxiliary. In the event that we need something extra, we have it actually coiled up here, but we haven't needed it yet.
And what kind of potting material do you use on your motors?
Oh, for molding? Plastic, actually, You can buy it in Hawaii, the poke bowls. It's like raw fish, right? And they come in these plastic bowls. So we were looking at it going, no, epoxy doesn't really stick to plastic, and that's a good way to have our waterproof connectors sit inside without falling during the molding process. And so we attached it, we put it inside, poured the epoxy inside, and then as soon as it's done, the plastic just peels right off the outside of the mold, or outside of the epoxy.
And was the same process done on the LED?
Yes, as well as our power mouse, which is 24 volts.
So you guys structured the LED system yourself?
Yes.
Like the cops?
The epoxy. They do get warm. It is, of course, in the aqua environment, so they self-cool themselves, as well as the motor drivers. If you notice, there are heat sinks protruding out of the epoxy, which are covered in a thin coat of epoxy to prevent conduction or electrolysis over here. They also water cool the motor drivers to really prevent failure.
You said your waterproof connectors you made yourself, did you say?
No, we purchased them from SureSeal.
So the LED lighting that you made, how is that structure architected?
Actually molded?
Well, no, I mean, you've got, it looks like you've got a grid of LEDs there, right?
Yeah, oh,
Is it like-
okay.
Are they all parallel, are they all serial, or are they all?
No, actually, there's 6 banks in there, 10 in parallel, in which case the 6, 10 are now in series, and that provides a voltage for us, so it only consumes 22.8 volts, in which case we put a bank of resistors to drop that voltage from 24, so that doesn't burn them out.
And you can tell you how the photo diode works.
You actually
control
control
the
the
light?
light dimmer, or get brighter or dimmer. We have a photo transistor here, and this change the resistance. So if we have hook up other transistor. So when it gets darker, this thing will detect it and kind of like brighter. Called
The gray thing, what does that do?
excuse me.
The big gray thing that's sticking there right next to your light.
Oh, it's
That's
camera.
Oh, it's camera. It's a wide view camera.
Okay. It's a fisheye lens, so we can see more.
So you can catch all that light.
You do catch a little bit of light.
I'm teasing you, it's more.
No, I mean, it is a factor. There's nothing wrong with asking it. Of course, they have its own LED system inside of it. So actually the light kind of tends to balance itself out as you turn it on.
Now, why did you make these lights automatic, dimming and brighting? What's the reason for doing it? Why not just have one?
Well, one, LEDs don't consume that much power. Well, with the amount of LEDs we have, it does get significant over time. So we figured, why waste power and also be a burden for the driver when he starts going down to deeper depths or into dark areas. These lights should be on as he needs them and not waste them if he doesn't.
And another thing too, we knew that the cave would be wrapped in a tarp or plastic material, which probably give off a lot of reflection. If they're on all the time, those are really, really bright. And if they're on all the time, we could get a lot of glare of that. So I put in the dimmer circuit on there, we only get as much as we need.
Is there a manual override for that, or is it just so the photodiode goes to the microcontroller?
The photodiode goes actually to it's actually connected to an open collector NOT gate.
Okay.
So we used it just logic to get that. The microprocessor will then send a signal to turn the NOT gate on or off.
Tell me about your buoyancy package. Is this that's just some foam that's encased in fiberglass?
Polystyrene encased in fiberglass and coated with the same epoxy resin we use to encase our motor drivers. Use a polymer to get that black color, and I did the graphics myself.
Okay.
So one last question for me. Where's the big red button?
Big red button to turn it off.
Yeah. So when it goes south.
And also, there's actually ready lights if the battery's connected, if the main's on, and the fuse is okay. So
Yeah, we have a separate fuse in the box.
protects the power system.
Yeah, to protect the system.
You told us what this stuff is, this contraption in the middle?
Yeah, sure. This is our 48 volt to 24 volt step down converter. This is the main competition fuse, 40 amps. which will connect to from here to our own power supply and go to our fuse internally.
And your tether, is it neutral, is it?
It's negative.
It's negative?
Yes. And the reason was mostly because of the cave. We figured if we had a positively buoyant tether, as you're entering the cave, it could get caught up in probably the top side of the cave and be potentially pulling on it, in which case it might damage the cave, which we didn't want to do. As of right now, it works really well by just laying on the ground as we enter and staying out of the way.
It doesn't create so much drag, it slows your vehicle down.
No, but then again, also partly the tether mate has a pretty big task too of making sure that myself as the pilot has enough slack, but not too much to where it is getting in my way. And also pulling it in so we can protect it, because it is the lifeline of the ROV.
I presume that has to flood before it goes negative.
Well, I mean, copper itself is already negatively buoyant, so the fact if you were to throw it in the water, this is actually just split sheet, so filling up the water is relatively fast. It's not after flowing one side of the pipe.
Okay.
Yeah, we're just about out of time.
Okay.
Thank you, guys.
All right.
Thank you.